So today we are going to be studying what I consider one of the most amazing data structures ever. There's some black magic somewhere in these data structures that they work at all, called Splay trees. Okay. Splay trees are binary search trees for doing lookups. And actually, that's all they are. They are just a binary search tree. And in fact, looking at a tree, you can't tell that it's a Splay tree. It's how you use it that makes it a Splay tree. And so they're used for lookups. And we have tons of different binary search tree data structures that are used for lookups. Red-black trees, AVL trees, something called scapegoat trees. 2-3 trees are not purely binary, but they serve the same role, right? And all of these have been designed to address a weakness in binary search trees, which is that if you allow your binary search trees to be arbitrary, you don't get good performance, right? We know that a balanced binary search tree gives you order log n time operations. Insert, delete, lookup, predecessor, successor, so on and so forth. But an arbitrary binary search tree can spend omega of n, can spend omega of n time on any of these operations, because if you're not careful about your insertions, you can end up with a binary search tree that looks like a path, and now it's a linked list, and so everything gets very slow. And so there are all of these techniques for maintaining balance. Things like AVL trees, red-black trees, 2-3 trees, and so forth. And they keep the search tree balanced at all times, and therefore they preserve the order and log n time operations. They do require, extra balance data. There's usually a bit or something stored in each node that tells you things about the shape of the tree and what you need to do to rebalance it. And they do these explicit rebalancing operations when the tree gets out of balance. The amazing thing about Splay trees is they say, we're not going to bother with any of that. Our Splay tree is just going to be a binary search tree with no extra info. So a node of this data structure is just a node with 2 children pointers and a key. Okay? And as a result, it's not balanced. But the amazing thing is that it's just as fast anyway. It achieves all the same order log n time bounds as the balanced binary search trees. It is amortized. Okay. And in fact, it achieves a lot more than just order log n time operations. There is a sense in which it is, how to say this? Well, you'll see this towards the end of the lecture, but basically, Splay trees have all sorts of other amazing time bounds on their operations, and there's actually a conjecture that the Splay tree is just the best possible data structure. Okay, and I'll formalize that at the end of the lecture as well, and if any of you want to do a project, proving that, that is certainly a fun project to do. Splay trees were invented in 1985 by Slater and, of course, and the title of their paper is Self-Adjusting Binary Search search trees. And they use the idea, which I've been putting forward in all of our lectures, of procrastination and making your work count. So the Splay tree, instead of aggressively staying balanced all of the time, right? Instead, the Splay tree doesn't worry about maintaining balance, but makes sure that if you do a lot of work looking for something in the Splay tree, then that also cleans up the Splay tree so that you reduce its potential and end up taking a small amount of amortized time and kind of putting the tree into better shape for future queries. Okay? And it does this, as I said, without tracking any information about the shape of the tree. Okay? So you don't keep it balanced. Instead, you adjust during searches in a way that releases potential that pays for any long searches. Intuitively, if the tree gets very imbalanced so that you take a lot of time searching, then your restructuring of the tree as a result of the search will make it not have that long path anymore. Okay. And there are two important intuitions or ideas behind this this notion of adjustment or of this potential function. One of which is path shortening. So if a search took a really long time, it's because you walked down a really long path of the binary search tree. So what you should do is make that path shorter. Okay. If the search is long, you can shorten the path so it's faster next time. Okay. And intuitively, right, you can think of the length of the path as a kind of potential, and that shortening it is releasing potential, which pays for the cost of doing the search. The problem here is that if you make one path in the search tree shorter, you're going to be making other paths longer. And so you have to be cautious in where you redistribute the length of the path so that you don't make things worse for other searches. A more sophisticated intuition is this idea of rebalancing. So let me put it on the next board. Instead of just focusing on one path, we're going to look at the whole tree, and we're going to talk about rebalancing the tree via rotations. And of course, this is what our other data structures, our other balanced data structures do, right? They see the tree is out of balance, they perform a rotation that basically takes a big subtree that's too low in the tree and sort of rotates it so that it's higher. And so you've shortened the tree overall. Okay. And so let me ask, why are paths in a balanced tree short? Which is a slightly weird question. You might think that having short paths is the definition of a balanced tree. But I'm going to look at another sort of aspect of it. Notice that when a search descends to the smaller of the two children, you are making rapid progress towards finding the item that you're looking for, right? How often can a search in a binary search tree descend to the smaller of the two children of a node. That is, the smaller subtree of a node. Well, what's the biggest the smaller subtree can be? Yeah?
1/2 of the original.
Exactly. Right? I'm in a tree of a certain size. If I go to the smaller subtree, I'm going to a tree that's half the size. Right? And that means it can happen only log base 2 of n times before you get down to a tree that contains only one item and is therefore the item that you're looking for. Okay. Going to the larger child could potentially be a problem if the larger child is very large, the larger subtree rather, is very large. So what we try to ensure is that in a balanced tree, each subtree should be at most 2/3 of the size of the tree, right? If each subtree is at most 2/3 of the size, then the same argument applies. You're decreasing the size of the tree by a constant factor each time, and so you can only descend log n steps before you reach a single leaf. So the problem with a bad search tree or a bad search happens if you have an excessively large subtree too frequently. And just to pick a word that won't get confused if I talk about large and small, I'll call that a huge subtree, right? Where its size is greater than 2/3 of its parent tree. And so these huge subtrees are where we get into trouble, right? Where they may cause us to take a long time to find our items. So what we're going to do is we're going to arrange for huge subtrees to have lots of potential. And when we encounter a huge subtree, we are going to extract potential. Now, we can't extract or reduce potential by getting rid of nodes. You can't just delete things from the tree and make it smaller. Instead, we're going to do it by raising that subtree higher. So if you've got a tree which is very big too far down, that's a bad situation, but you know that the direct children of the root are going to be very large, and so if you move bigger trees up when you hit them, that's going to extract the potential that you need. Okay? And we're going to do this via rotations. So let's talk about rotations a little bit. So rotation is something that you saw whenever you learned about balanced binary search trees, right? The standard notion of a rotation is where you have a binary tree, where you have 3 subtrees, a pair of nodes, and you perform a rotation that moves one node up to become a parent of what was previously its parent. Whoops. Sorry, let's try again. Okay, so this is a rotation. And you'll notice that it is order preserving, right? The subtree B is the items that are between x and y. And so when we perform a rotation, B is still the items between x and y. So everything is still in the proper order. Okay? But this is sort of a good rotation to do if tree A is huge, right? Because tree A gets higher up in the overall tree and things look more balanced. Okay? Now A has to be compared against both B and C instead of only being compared against B in this other state. So this is the type of rotation that everybody was familiar with. But it turns out that using these rotations for rebalancing per the goals of the Splay tree, they don't work. Okay? These rotations, which are called single rotations, right? They unfortunately cause as many problems as they're solving. As you're sort of bringing one thing up, you end up pushing other things down in a way which may lead you in as bad shape as you were before. And so one of the key insights of Slater and Tarjan was to come up with a rotation mechanism that would actually work to release potential from your tree. And these are called double rotations. Okay. Now there are two types of double rotations because things get more complicated if you are looking at sort of two layers of rotation. So here is one starting position. Whoops. Okay, so here we have a binary tree where I've written out more layers. Again, the capital letters are whole subtrees. So a double rotation will take this, and it's going to bring x up to the root. And that is going to split y and z. Okay. So this is a double rotation. You now look, instead of just looking at 2 steps of a path, you look at 3 steps, or 3 nodes on a path. And this brings the grandchild up to become the root of the entire tree. Okay? And I mean, visually, this appears to be nicely balancing things, right? It got all of A, B, C, and D onto the same level. Remember, of course, that these 4 subtrees may be very different in size. So it may not actually be balanced, but this does work well. And just because of the shape, this is known as a zigzag double rotation. And this is actually the result of this double rotation is the same as you would get if you just did 2 single rotations of x. So rotate x to y, and then rotate y to z. So if this were the only story, then we wouldn't need to talk about double rotations. But what can happen in, sorry, this is one way. What can happen in another situation is if the path has 2 steps in the same direction. And a double rotation here sort of moves everything as a group. And this is different from what you would get if you did 2 single rotations of x. Okay, so they are making a change. It seems like a pretty minor change, but it completely changes what happens in the data structure overall. Okay? Now this one you'll notice is bidirectional, right? It moves you things from a right moving path to a left moving path or vice versa. It's known as a zig-zig double rotation for obvious reasons. Okay? There are 2 mirror cases, the zag-zig and the zag-zag, which I won't draw, right? But you can infer what they are. They're completely analogous. Okay. So this double rotation is a way of rebalancing a tree locally, just like the single rotations that you use in standard in the more familiar balanced binary search trees. Okay. But this turns out to be the only operation that you need in order to define splay trees. So starting from these double rotations, they define a notion of splaying a particular node x. And this simply means to move x, or this means to, move x to the root via double rotations, and possibly one last single rotation if the depth of the node was odd. Okay. Yes?
Sorry, is zig-zig not equivalent to 2 single rotations?
A zig-zig is not, thank you. It is not, and it is a good exercise for you to figure out what the tree will look like if you perform 2 singles. It comes out different. Okay? Now, looking at it, it's not at all clear why the difference matters, or why this double rotation operation is better than 2 single rotations, right? But it turns out that if you use these double rotations, you can improve these amazing things that just aren't true if you use single rotations. And so again, I said there's some black magic here. It's very hard to sort of point and say, oh, that's the reason that this is working. Okay. All right, so this operation is the self-adjusting operation for splay trees. Okay, so the way you implement search for a node in the search tree is first you find it, and of course if it's in the tree, great. If it's not in the tree, you're going to land on the predecessor of the node, or possibly the successor, depending how you break ties, right? So you perform this find operation, and then you splay the node to the root. That's it. Okay. This is the whole splay tree algorithm. Okay. No fancy data structure, right? It's just a tree, no extra information. The only thing they're changing is that after you do the search, you bring the item that you looked for to the root. Yes?
Is recursive function?
You don't generally talk about it recursively. You generally do it iteratively, right? You start at your node x, you perform a double rotation, which moves x up. You still are on node x, and you perform another double rotation to move x up another 2 steps, and you just keep doing this until you get to the top. Okay. Yes, question? Or no, that's just a figure exercise. Okay. Other questions? So, not too hard to, yes?
What do we do if, like, x is just one little bit below?
So that's this possible one last single rotation. Okay? This happens if x has an odd depth, right? Each double rotation will move it 2 steps up. So if its initial depth is odd, it will eventually become a child of the root, and then you just do a single rotation to move it to the root. Okay? Actually, that isn't too important. You could just leave it as a child, and all of the theorems would still be true, but it would actually be a lot messier to talk about. Okay? All right, and this is the magic. Okay? If you do this, then all of a sudden, your binary search tree, which you're not trying to balance at all, has order log n search time. And I will later show you how to implement insert and delete, also by using Splay, and those also take order log n time. Okay? But for now, we're going to focus on searching and analyzing the behavior of search. Okay? So I'm actually going to give you a pretty general analysis. I could give you a more specific one if all I wanted to prove was this order log n time bound, but it turns out if I generalize the analysis a little bit, I get all sorts of other cool results. But again, I'm only generalizing the analysis. There's no change to the algorithm, because how could the algorithm be any simpler than this? So in order to analyze splaying, I'm going to assume every node x has a weight w sub x. And all I'm going to require is that they be non-negative. Okay, or sorry, they'd be positive. Okay, 0 would not be good. Okay, and this is just for analysis. Okay, the data structure has no idea what the weights are. I'm just inventing them to prove things. Okay. For now, and for intuition, you can assume all the weights are 1, but we will use the more general weighting to prove some other cool things. Now I'm going to define, actually, before I go further in the analysis, let's talk intuition for a minute. Is there any intuition at all for why splaying something to the root after you search for it might be a good idea?
Yes.
Repeated searches on the same element will have very low cost.
Exactly. This is path shortening, right? If I search for something and I splay it to the root, then the next time I search for it, it's going to be at the root. It won't take any time. Which is lovely, except I push something else out of the root, right? And if I end up splaying lots of things to the root, I'm going to push down the things that I searched for originally. But at least recent searches will still be up high. So actually, splay trees have locality of reference, for those of you who are interested in systems, right? And I'll come back to that, and we can prove things about it. But yes, splaying kind of has this path shortening intuition. And also, if you look at the zigzag case, it gives you a little bit of this kind of cutting paths in half intuition, right? It's taking, if you look at splaying, if you have just a path and you splay it, its length shortens to half from n to n over 2, thanks to to what happens with these zigzag rotations. Okay. So now we're going to be formalizing that intuition, and so we're going to define the size of a node to be equal to the sum over all the descendants of that node of the weight of the descendant. So you're just adding up all of the weights in the subtree in order to get the size of the subtree. And finally, we are going to define, and again, what is this number if all the weights are 1? It's just the number of nodes in the subtree, right? Very natural. Now we define the rank, R of x, to be equal to the log base 2 of S of x. and that base 2 actually matters for the analysis. Okay? And so what intuitively might the rank correspond to? What would the log of the size of the subtree reflect? Yeah? Yeah, if it were a balanced tree, then the rank would be about the depth, right? Of course, the tree isn't necessarily balanced, but we can think of this as sort of the height of the best, or of a balanced version of the subtree. Okay. And finally, we can define our potential function, phi. And again, I think I said this before. In amortized analysis, pretty much all the creativity happens in thinking of the right potential function, right? Once you have the potential function, you just do the calculations and everything works out. But thinking of that potential function that's where you can have some real creative inspiration. And actually, when I moved into my office in graduate school, I think that I ended up with Slater's desk, because when I opened the drawers, it was full of these pads of papers that had little trees drawn on them, and like sort of ideas about potential functions. So I have no idea how they came up with this potential function. In your problem set for this week, I will give you sort of a rationalization for it, sort of why it kind of makes sense to get, but I don't know how they thought of it in the first place. The potential function is equal to the sum over all nodes of the rank of that node's subtree. Okay. Why? Because it works. Okay. Once we have it, we can develop a little bit of intuition. Okay, so remember what I said at the beginning was that out-of-balance subtrees are ones where there are really huge subtrees very low down in the tree, right? So if you have a huge subtree low down in your overall tree, what is that going to do to the potential function? Yes.
I think you should make it pretty big because there's a lot of these things that are descendants of a lot of other nodes.
Yeah. In particular, if this huge tree is very low, there's a whole path to that huge subtree, and every node on that path has lots of descendants because it contains that huge subtree. So every node on that path will have large size, and that means that every node on that path will have large rank. So a badly unbalanced subtree, a badly unbalanced tree is going to have a large potential, which is what we want. Okay. If you have a low, huge subtree, that implies that all its ancestors have a large size, which implies that they all have a large rank, and that implies that phi is going to be large. Okay. If, on the other hand, you have a balanced tree, what does its potential look like? Well, you have lots of little trees, but they don't contribute a lot of, right? They don't contribute to a lot of other trees, right? So the little trees, there's many of them, but they're all small size. They don't matter very much. You only have a few large trees, large subtrees at the top, so they will have large rank, but there aren't very many of them. So overall, a balanced tree will have a low potential. Okay? Okay, so now that we have these definitions, we can prove the critical access lemma. Okay. Which is that, again, this assumes these arbitrary weights x. The amortized time to splay x given your current root, or yeah, that's good enough, t is 3 times the difference in rank between the two nodes plus 1. And again, this is basically the only theorem you need to prove about splay trees. Everything, or the only lemma that you need to prove. Everything follows from this lemma. Okay. Just to understand what this means, remember, what's the rank of t by definition? What's the rank of x? Yeah.
Optimal size for the subtree.
Yeah, it's sort of the optimum size subtree, right? So you've got the whole tree, and you imagine it's optimally shaped, right? So its depth is going to be about log n, right? And then you've got this other subtree that x is the root of, and it is also of optimal depth, of optimal size, optimal height. And so actually, in a sense, this difference is sort of what you would imagine the depth of x should be given the size of its subtree, right? So really what this is saying is that if things were balanced, this would be the real cost. And instead, this turns out to be the amortized cost. And so we can write this a different way, right? The difference in ranks, because these are both logs of sizes, it's the log of the size of the root, the size of the whole tree, divided by the size of the tree rooted at x plus the 1. Okay? Okay, and so we just ran through this intuition. That R represents the height of the node when you're in a balanced tree. And that means that the amortized time is just the difference, or is just the optimal depth, or the ideal depth of x. If it were in a balanced tree. But of course, it isn't in a balanced tree. It's in whatever tree the splaying algorithm produced. Nevertheless, from an amortized sense, from an amortized perspective, it works out just fine. Okay. Another intuition. Okay. If x really is high in the tree, if x is high rank, i.e. a large subtree, we want it to be high in the tree. Right? And if it is high in the tree, then things are great because the real search time is small. Right? On the other hand, if x is very low in the tree, then the real search is slow. But why is that okay? How do we pay for this slow real search? Yeah?
The potential changes enough to make up for it?
Exactly. And the potential changes in the right way, right? The x subtree is raised by the rotations. And that means there are fewer descendants of x, fewer ancestors of x, my bad, which means that there are fewer large ranks, which means that phi drops. And that decrease in potential pays for the large real search time. Okay? Now, I will squeeze in, because it's very fast, an immediately corollary. Let's set all the wx to be equal to 1, as I said, the simplest case. Okay? If all the wx are equal to 1, then what is r of t? Yes?
Log in.
It's log n. And what can I say about r of x? And the thing I have to be careful about is that I don't want r of x to be too small because I'm subtracting it. So can somebody give me a lower bound on r of x? Yes.
Probably 0,
Wow.
because s of x is at least 1.
Exactly. Right? So r of x, which is just log of s of x, is at least the log of wx because x is in its own subtree. So the size is at least wx, right? Which in this case is 0. Okay. So this access lemma immediately tells us that the amortized time to splay a node to the root is log n. Okay. Now, that's the amortized time for the splay, but I told you the amortized time for search is going to be log n. Can anybody sort of make that connection for me? Yes.
The search time is on the order of the access because every time you look it up, like it's the same path.
Exactly. Right? The search time is smaller, or is actually equal to, the splay time, right? Because it's just the length of the path, right? The time to do the splay, the real time to do the splay is just the length of the path. Similarly, the real time to do the search is the length of the path. Same real times, and therefore same amortized times. Clear? So what I've shown you is that as soon as we've proven the access lemma, we immediately have this result that splay trees are as good as balanced binary search trees, even though they're not balanced. Clear? All right. So, important little detail. In order for this to be true, you have to splay even when x is not in the tree. Right? If you search for something and you don't find it, you might think, shucks, don't splay. But since you want the search time to be equal to the splay time, you have to do the splay even if you didn't find what you were looking for. Okay. All right. So all that's left to be done is to prove the access lemma. And that seems like a very good time to take a break to sort of maintain the dramatic tension for as long as possible. So let's grab a couple minutes, stand up, jump up and down, say hello to somebody, and we'll resume in a couple minutes. All right, let's resume. I'm sure that we would be getting up to like 100 or 200 push-ups if I left the break going, but we have to get back to theory, unfortunately, so you'll have to finish your 100 push-ups elsewhere. Okay, so now we're on the analysis, the actual math. Okay. And I mean, this is typical of the class. Like, I always like to have just a little, to squeeze the math into the end because it's not the interesting part, right? I care much more about the sort of intuitions, but sometimes you just have to do math. So let's look at the amortized cost. So that's the real cost plus the, wait, what is that saying? Oh yes, the claimed amortized cost. We haven't proven it yet. Actually, sorry, I made a typo here. I think, well, no. Hold on a sec, I have a typo. Let me just think for a minute. Right, that's what I forgot. So we are going to look not at the amortized cost of the entire splay, but simply the amortized cost of one doubled rotation. Right? The splay is just a series of double rotations followed by a single rotation. Here's the single rotation. So we'll just think about the double rotations, and the amortized cost of the entire splay is just the sum of the amortized cost of the double rotations that we perform. Yes? And so that double rotation, I'm going to do the zig-zig case, because that's the harder analysis where you have to be more careful. You can look at the zigzag case in the paper. I'm just going to draw it here for easy reference. Okay, so we start here, okay, with certain ranks of the various nodes, and we perform this double rotation, which brings x up as a replacement for z. We have other subtrees. And I will call these the prime ranks, the ranks after the double rotation. Okay? Now, which of these primed ranks are different? Where do ranks change as a result of this one double rotation? Yes?
X, Y, Z.
Only x, y, and z, right? Everything in these subtrees, the sizes aren't changing because the trees aren't changing and the ranks aren't changing. Similarly, if z is not the actual root, but there's parents, they don't see a difference either because the size of this entire subtree that z roots is still the same after the rotation, right? So in order to talk about the amortized cost, all we need to look at is the real cost, which is 2 rotations. I'm measuring in rotations, okay, plus the change in potential. And what is the change in potential? Well, we just said that only x, y, and z change in ranks, so we take the new ranks and we subtract the old ranks. Okay. Now, can we do any simplifications in this formula? Yes?
R prime X is the same as RZ.
Right. This is what I was just saying, right? The tree as a whole doesn't change in size. So the size of the root is unchanged, even though the root is different. And that means that the rank of the root is unchanged. Okay? So that means, in particular, that r prime of x is equal to r of z, and we can go ahead and cross out two terms in our formula, right? So this is equal to 2 plus r prime of y plus r prime of z minus r of x minus r of y. All right, that's nice, but now I want to simplify further, but basically by not thinking about y. So I'd like to get some upper and lower bounds on r prime of y and r of y so that I only need to think about x and z. Okay, so how can I do that? So I'm interested in r prime of y, right? The rank of this whole subtree. Can I upper bound that without referencing y? Well, this subtree is inside of the x tree, right? Which means that its size is no larger, which means that its rank is no larger. So I can upper bound r prime of y by r prime of x. Now I'd like to play a similar trick here with the rank of y, right? So, but now y is being subtracted, right? So, and also I need to look at the original tree, because it's r, not r prime. So now I want a lower bound on the rank of y. Where can I find that?
Yes. On the rank of x.
Exactly. Okay. And I'm going to gather some terms together. I have an r prime of z minus r of x. And I also have an r prime of x minus r of x. Why? Well, we'll see in a minute. Okay. So you'll notice that this last term is already in the access lemma. Right? The access lemma says 3 rank differences. Here is 1 rank difference. Okay. So all we need to prove is that what's left is the other 2 rank differences. Right? It's sufficient to show that 2 plus r prime of z minus r of x is less than or equal to twice r prime of x minus r of x. Because if I combine this with 1 more r prime of x minus r of x, then it shows that the actual difference is 3 times the rank difference, which is what we need for the access lemma. Is that clear? Again, remember, I'm adding up the amortized costs of all of the double rotations. So if each double rotation has an amortized cost which is 3 times the difference in ranks, well, when I add all of those up, I get a telescoping sum, right? I change r of x to r prime of x, right? Then I change r prime of x to r double prime of x, but I subtract off r prime of x, right? And so everything telescopes up until I have just the difference between the original rank of x and the rank of the root of the tree. A question?
So when you're substituting y in the r prime, are you using upper bound and lower bound in the r?
Yes, I'm doing one of each, right? So here I'm adding r prime of y, and so since I'm doing upper bounds here, in order to preserve an upper bound, I need to use an upper bound for r prime of y, right? However, here I'm subtracting r of y, and so to get a legitimate upper bound on the entire sum, I need to put in a lower bound on what I'm subtracting. Okay? Okay. Sorry, I just remembered I got asked a useful question during the break, but I don't remember what it was. Which is why you shouldn't ask me questions during break. You should ask them during class. Does anybody remember? Do you remember what the question was?
Push-ups?
No, it's definitely not about push-ups. It was an actual technical question. Yeah?
I think it was about like which elements do we splay with, like if we don't have.
Ah, yes. So I told you that you need to splay even if you don't find the item, but then what do you splay? The answer is your search is going to end up at failing at some leaf node, right? Or it's at some internal node. That is the node that you splay, the one where you give up the search, because that's the time it took you. Okay, and that's what you have to pay for by splaying. Okay, thanks. Okay, so all we have left to do is to prove this this upper bound that remains. Okay. And if I rearrange this, right, what I need to show is that r prime of z plus r of x minus 2r prime of x is less than or equal to minus 2. Okay? So this is just rearrangement. Here I had r prime of z minus r of x, but now I bring 2 r of x's over to the left-hand side, and that turns it into a plus r of x. I then subtract off the 2 r primes of x, and I move the 2 to the other side. Okay. But now, this is where all of this built-up dramatic tension gets resolved. Let's unpack this according to its definitions, right? This is the log of s prime of z, right? Minus, over here, a log of s prime of x. So subtracting logs is about division. And I also have a log of s of x divided by s prime of x. Yes? Now, can we figure out where these are in the pictures? So I have a, let's see, did I draw those things correctly? Yes, so x moved to the root, right? So these s primes of x are really just the whole subtree, the whole tree, right? Now, where is s prime of z and where is s of x? Like, which parts of the picture determine s prime of z and s of x? Yes.
A, B, and C, and D.
A and B and C and D, but let's be specific about that, right? So s prime of z here is determined by where z is after the rotation, right? And s of x is determined by where x was before the rotation, right? So what is noticeable about these two subtrees? Yeah.
They add up to make all the nodes except x, y, and z.
Exactly. They're disjoint. Right? They're basically the two halves of our entire tree, aside from the root node. Okay? They're everything except for y. Right? All right. Whereas s prime of x, right, again, this is x after the rotation, so that's the whole tree. So what are we measuring? we're measuring one fractional part of the whole tree and the other fractional part of the whole tree, right? So this is just equal to the log of A plus the log of, well, basically 1 minus A, if I don't worry about y, and if I recognize that y has some weight, it's still an upper bound, right? Where A is just this fraction. Okay. Now, I don't know what number A is, but it doesn't matter, because I can just ask what is the maximum possible value for this expression as a function of A, right? Notice that A is between 0 and 1. Right? And so this is a calculus problem to minimize, to maximize this. And if you think about it, you're just maximizing A times 1 minus A. Where is that maximized? At 1/2. A equal 1/2, which is to say that this is equal to the log of a half, which is minus 1, plus the log of a half, which is also minus 1, which is minus 2, which is what we needed to show. Okay? So we're done, right? We've proven that the amortized cost of a double rotation is 3 times the change in rank of x. Okay. And since each double rotation has a cost of 3 times the rank change, it means that a splay has a cost of 3 times the rank change. Any questions? Okay. So again, I can't really draw a lot of intuition out of the math. It just works. I developed a problem in the homework that tries to make it a little clearer why it works. Okay. Now, there's an important caveat here that we're working amortized. Right? We're talking about the amortized cost of operations, where we have a sequence of operations. And what we showed last time is that the sum of the real costs was upper bounded by, or was equal to, the sum of the amortized costs plus the final fee minus the initial fee, right? There is this additive term, right? And if we only do one operation, the real cost might include this whole additive term, right? And it might be very large. Okay? But let's think about what phi n and phi 0 can be. Okay? What is the largest possible phi? Given my definition. Yes.
And log n?
N log n, that's correct, right? So remember that phi is a sum of ranks. Each rank is a log of a size. The size is at most n. More generally, if we write W for the sum of the weights, right, we can just notice that every size is at most W, which means that every rank is at most log W, which means that phi is at most n log W. Okay. What is the smallest possible phi? Can we lower bound the potential? Yes.
3n?
3n. How come?
Because in the last layer we can have like 1 times n plus 2 times n over 2 plus 3 times n over 3.
So you're assuming you're sort of adding up the various subtrees that are emerge from a balanced tree. But what if the tree is not balanced? Right? We really need something that applies to any tree at all. Okay. Well, again, let's look at it in terms of individual nodes, right? If I want to lower bound on the potential, can I lower bound the potential from an individual node? Or start by looking at this. How do I lower bound the size of one node's subtree? Yes. It's not negative. It's bigger than 0, but we can say more than that, right? What is in the subtree rooted at x? It's not empty, right? X. So the size is at least wx, right? And that means that the rank is at least log of wx, which means that the minimum phi is at least the sum of the log of the wx's. If I put these things together, it tells me that phi n minus phi 0 is at most n log w minus the sum of the log of the wx's, which can also be written as the sum over all of the x's of log of w over wx. Okay. But this is actually a term that shows up in our access lemma. This is the cost to splay x to the root, basically. Okay. So there's an error term in our potential function, sort of the gap between the amortized and real costs. But we can bound the error by the cost of splaying each node once. So after you have splayed every node of the tree, the real cost and the amortized cost are about the same. Right? So if you only do one splay, it might cost n and give you a negligible amortized cost. But as long as you splay every node at least once, you can use the amortized costs instead of the real. They're a valid bound on the real costs. Okay? So that's not a very damaging caveat. Okay? All right, good. This is pacing well. So now that we have proven the access lemma, we can apply it. Okay, we've already said that if we set all of the wx is equal to 1, then the access lemma says that the amortized splay cost and search cost is order log n. So, and this is known as the balance theorem. Says that splay trees are just as good as balanced binary search trees, even though they're not balanced. Okay. But we can do a lot more, okay? Because again, the access lemma was proven without any assumptions about the weights. Okay, so I can pick different weights and get a different result about the amortized cost of doing searches. Okay, so to show how that can be useful, let's talk about static optimality. So the question of static optimality concerned data structure researchers for a while. They said, suppose that you know the access frequencies. pi are known. Okay. That is to say that there are PIM accesses. Sorry, these should be x's. P sub x m accesses to node x among m accesses. So suppose you know this in advance. The question is, what is the best static binary search tree for this particular access frequencies? Okay? So if I told you that, this node is going to be accessed a lot and the others very rarely, what should you do in building a binary search tree that's good for those accesses? Yeah.
You should put the ones that you have to access a lot near the top.
Exactly, right? More popular items should go to the top of the tree because then the search for them will be short. In the extreme case, if there's only one item that's ever accessed, you put it at the root and you access it in constant time. Okay. Now there's some tensions with that idea if you're trying to make a binary search tree, right? Because you also have to obey the ordering constraints, right? Also, you can't put all the popular things at the root because there isn't room, right? They have to sort of spread down. Okay? But you can imagine that you might want to put the most popular thing at the root and then the two next popular things as children, except they might both be on the same side of the root, and then you can't have both of them as children of the root. But you can imagine this sort of optimization problem of figuring out the best shape of a search tree for the given access frequencies. And this is related to a problem called Huffman coding, if any of you have ever seen that, right? And there's a theorem that says that the best possible static tree has average access time equal to the sum of p sub x times the log of 1 over p sub x. Okay? And the intuition behind this is that, well, if you have an item that's accessed more than half of the time, you should put it at the root. Okay? Of the remainder, if you have items that are accessed, more than a quarter of the time, well, there's room for 2 of them among the children. Right? Items that are accessed an eighth of the time, they can be the grandchildren, and so forth. Okay? And so this log is basically how many nodes you have at a given level of probability that you can occupy in order to make the accesses to those nodes be fast. Yes?
Is that an expression for entropy as well?
And yes, this is fascinating because it is connected to the entropy of the access distribution. Somewhat surprising, although not entirely surprising after you notice it, but it definitely surprised the first person to discover it. If we dust off our access lemma, let's use the access lemma, but set w sub x equal to px. So if the weight of node x is p sub x, right, what is the total weight, w? It's just 1, right? Now the access lemma says that the splay and search cost for x is the log of w over wx. In other words, it's the log of 1 over px, right? And so if you're going to do px times m such searches, the overall search cost is the sum of mpx times log of 1 over px. In other words, it is m sum of px log 1 over px. So splay trees are statically optimal, even though they weren't trying. Okay. Even though splay trees don't know the px's. Right? We only introduced px in our analysis. They don't show up anywhere in the actual data structure. Okay? Let me tell you another one. Okay. So there was this other idea in data structures of what's called a finger. So this is sort of approaching this idea of locality of reference. Okay? If you expect that you're always going to be accessing the same part of a binary search tree, then it might not make sense to start at the root, right? If what you're accessing is always somewhere down at the middle. So people introduced this idea of a finger, where you just put a finger on some node in the search tree, and you start your search from there. This is a little bit odd because it means that at the start of your search, you might go right, or you might go left, or you might go up. Okay? But if you can start the search near the item that you want to find, that search should take less time. Okay? So people introduced, people proved the so-called static finger theorem. Okay? And they said, imagine that you have a particular fixed tree. And again, you're optimizing. Suppose you know the access sequence, okay, in advance, and you get to pick your favorite static search tree and also the finger that you're going to start with. Okay? And you just build the optimal one. Okay? The access lemma can be used to prove that splay trees are as good as the best static tree with finger. And to prove that, you just use a different potential function. You define the weight of node x to be 1, I don't know who came up with this or how, 1 plus the distance from the finger in the list of items, the rank difference between x and the finger node. And if you do the calculations, you find out that the cost of a search is order of the log of this difference in ranks, which is optimal. Just like searching in a binary search tree, the best thing you can do is log n. Similarly, in terms of a finger, the best thing you can do is log of how many nodes there are between you and the finger. There's working set optimality. So this really gets at locality of reference. Imagine, you're searching through a search tree that's so big that it doesn't all fit in memory, right? But you might want to have a cache of the recently searched items, right? And build a little search tree on the recently searched items so that you don't have to look over the entire search tree. Okay? So intuitively, you can imagine creating a cache that should let you find item x in time, which is sort of proportional to the log of the number of items you've searched for since the previous search for x. Right? In other words, if you just make a search tree of the right size, that's big enough to hold the right number of recent items, then you can find x in that little search tree instead of looking in the whole search tree, right? And splay trees match this. Even though they don't know what your access sequence is, they don't know how long ago it was that you last asked for, they don't have any memory of that, but they achieve this search, okay? Another really weird result, okay? If you have a binary search tree and you search for the items in order, smallest to largest, okay, what's the total cost of that search in a standard binary search tree? Well, each of them costs log n, right? So it's going to be n log n. But if you really want to list all of the items in a binary search tree, how long does it take you? It takes you O of n, right? You can just walk the tree, right? Well, if you access all the items of a search tree in order, splay trees accomplish the whole thing in order n time. Okay. So basically, splay trees can do everything, right? They match the performance of every other data structure, and they match all the data structures at the same time, right? At the same time as you have working set optimality, you also have static optimality and finger optimality. Despite the fact that you haven't told the splay tree which of those you care about, you get them all for free just by changing your analysis without changing the data structure at all. Okay? Now, there remains one giant question around splay trees. This is what is known as the dynamic optimality conjecture. And it reflects the natural conclusion that you draw after seeing splay trees, which is that splay trees are just the best, right? So the dynamic optimality conjecture says that splay trees will do as well as any other strategy for maintaining a tree and modifying its shape whenever you like using rotations. Okay, so basically, the conjecture is that splay trees are the optimal way to rotate trees to give you the fastest possible access to any sequence whatsoever. This question is open, right? Eric Demain on the 5th floor has contributed some really important work to this question. They developed something called tango trees, which are not splay trees, but are within log n of the optimum of any data structure. And in doing so, they developed some really interesting analytic techniques that might someday, again, a lot of data structures still believe this conjecture, even though it hasn't been proven yet, and even though at the moment, tango trees are sort of have this theorem that we don't yet have for splay trees. Okay? So that's the story of splay trees. Next time, I need to fill in how do we do insertions and deletions. It's very easy. It'll take me 10 minutes. And then we will start talking about how to use, so far we've only looked at pointer-based data structures. In the next couple of lectures, we'll look at how to use indirect addressing to get better performance for basic data structure operations. Okay? We have the first problem set due, and that means we have the first grading party. Those of you who have volunteered and been taken as graders for this week should have an email saying so. You should gather with the TAs at the back of the room so that you can go and sort of start the grading process together. In general, I want you to grade together for a while until you establish the kind of rubrics that are necessary for the problem that you're grading, and you'll be doing that with the TAs. Then you'll go off and do the rest of the grading by yourselves. I will see you on Friday.